So let's make a start. I'll introduce Debbie for our first talk of the year. So Debbie is an electrochemist and ARC Future Fellow in the School of Molecular and Life Sciences at Curtin University. She completed her PhD at the University of Oxford and then spent a short time as an intern for the Schlumberger Cambridge Research before arriving at Curtin University in 2009 as a Curtin Research Fellow. So since arriving at Curtin, she's been awarded a number of grants, and including an ARC Discovery Early Career Research Award, an ARC Future Fellowship, and this year she's just been promoted to full professor. So yeah, she's definitely made great headway in the last few years. Not only is that, she's also recipient of multiple international and national awards, including the 2021 Lefebvre Medal from the Australian Academy of Science, the 2021 Analyst Emerging Investigator Leadership from the RSC, and the RACI medals and lectureships from 3 divisions, and also the overall Chemistry Rene Memorial Medal in 2019. So that's quite a list you're building up there. I'd love to see your cabinet sometime. Yeah. But yeah, so let's make a start. So thank you very much. There's that.
So first of all, thank you very much, Terry, for that lovely introduction. So the title of my talk today is Understanding Fundamental Behaviour of Ionic Liquids as Electrochemical Solvents. But when Terry actually advertised my talk on LinkedIn, he used a different title, which was How Ionic Liquids Are Revolutionising Sensors. And I quite like this title, so I might use it for some of my future talks. So as you can see from the title, I'm going to be talking about ionic liquids, and specifically how we're using them in gas sensors. And if anybody is on Twitter, and you don't follow me already, please follow me, and I'm happy if anyone wants to tweet pictures from tonight as well. So this is my first seminar of the year. Last year I gave 20 seminars, but this one was an invited seminar because I got last year awarded the RACI PhysChem lectureship. And the lectureship is for early career researchers up to 10 years post-PhD to get the opportunity to travel around Australia and go to as many chemistry departments as possible, up to about 20, to give seminars on their research and make lots of collaborations with people. Obviously, COVID has affected this a little bit, so we've had an extension till the end of this year, and I'm hoping in the second half of the year I'm going to be able to go to a few cities and give some seminars. So before I start this seminar today, I would like to acknowledge the traditional owners of the land on which we meet, which are the Whadjuk people of the Noongar Nation, and I pay my respect to their elders past, present and emerging. So I'm actually going to begin my seminar with a video, and as Terry mentioned, one of the medals that I got last year was from the Australian Academy of Science, and they required me to make a video about my research, and I thought it would kind of be a bit wasted if I don't show that, so I'm going to show that to give you a kind of a bigger introduction about the big picture of my research, and then I'm going to go into some more of the details.
There's been an explosion and police have rounded up suspects. Imagine if they had a sensor that could instantly detect explosive residue on clothing. That's just one of many potential applications for the work of Associate Professor Debbie Silvester Dean. She's an expert in a class of materials called ionic liquids.
We can design the chemistry of the ions to selectively absorb gases to enable their detection.
And not just for criminal investigations. She hopes the sensors could be used anywhere people are exposed to toxic substances.
For example, in painting, fumigation, fuel filling, refrigeration and mining.
In fact, Associate Professor Silvester Dean is already trialling the technology on mining sites in Western Australia. The sensors themselves are smaller than a fingertip and cheap to make. That means they could end up having a role in our everyday lives.
You can plug a sensor directly into your mobile phone and you can monitor your local air quality. So you can decide, is today a good day to go for a run?
She thinks within 20 years, people will be attaching wearable electrochemical sensors directly to their clothing. Associate Professor Silvester Dean is a recognised leader in her field, but the only member of her family to ever go to a university.
And I think it's very important for young people, especially young girls, who are in a similar position that I was in, to know that there is a place for them in science, no matter what their background.
Associate Professor Silvester Dean has been awarded the Lefebvre Medal for research in chemistry.
So we're looking at ionic liquids as replacement solvents. So maybe about 10 or 15 years ago, when I first started working with ionic liquids, I asked the question, can room temperature ionic liquids replace conventional aprotic solvents in electrochemistry? And if so, do they have any particular advantages? And so for those who are not familiar with ionic liquids, I'd like to first start off by talking about salt, so the normal table salt that you might put on your chips. So we're all chemists. Hopefully we should know that salt is made up of sodium chloride. So you have a sodium cation and a chloride anion. And the ions are fairly similar in size and they pack very well together in this lattice structure. And so the melting point of sodium chloride is very high, about 800 degrees Celsius. But now if you change the chemistry of the ions, and particularly if you make one of the ions, in this case the cation, asymmetric, so for a quaternary ammonium chloride, you can see that we've reduced the melting point from 800 degrees down to about 80 degrees. And the reason for this is because we now have a disrupted lattice structure. So we can push this even further and we can make the, both the cation and the anion larger and more asymmetric, disrupt this lattice structure even more, and that's where we end up with room temperature ionic liquids. And ionic liquids are similar to salts in that they're made up entirely of cations and anions, but as you can see, the chemical structures of these ions are very different to sodium chloride, so much larger molecules. And because of this, they have very poor lattice packing. So this particular example, which is an ethyl imidazolium with an NTF2 anion, has a melting point of minus 10 degrees Celsius. So at room temperature, it's very clearly a liquid instead of a solid. And so we can think of them now as solvents rather than just as electrolytes that you dissolve into a solvent. So they're composed entirely of ions, normally a bulky asymmetric organic cation and a weakly coordinated inorganic anion. As I mentioned, melting points can be changed, and room temperature ionic liquids by definition are liquid at 25 degrees Celsius. But noting that you may also see this definition of an ionic liquid, which has a melting point below 100 degrees Celsius. So we're really interested in the ones which are liquid at room temperature, and compared to a traditional solvent, they are non-volatile. So they won't evaporate, and this gives us advantages, particularly in our kind of sensors where we use very small amounts of them. And they're also very highly thermally stable, and they can survive temperatures up to and above 180 degrees Celsius. So you can even perform reactions in ionic liquids at high temperatures, which you can't do in a lot of the volatile organic solvents. And they come in with a number of different cations and anions. These are some of the common ions. I was at a conference once and told there were theoretically up to 10 to the power of 18 different combinations possible. But in reality, there's about 500 or so commercially available, and obviously there's people that make more unique ones in their own labs. So the ones we usually use for our electrochemical experiments are often based on imidazolium cations or pyrrolidinium, pyperidinium, and these longer chained tetraalkyl phosphoniums and ammoniums. And so each cation is paired with an anion. The ones which would technically be ionic liquids, but not room temperature ionic liquids, would have some halides. But as you get to more larger structures, such as this FSI or the NTF2, you can have very liquid ionic liquids at room temperature. And they've been investigated as a replacement electrochemical solvent since about the beginning of the century. And I'm really pleased to say that in the last few years they have been commercialised in various applications, including batteries, supercapacitors, actuators, and sensors. And the sensor commercialisation has been with a company that I'm working with, and I actually just finished a call with them just before this meeting. So it's actually really good that we're moving from just understanding properties of these and moving into real applications. So if we think about ionic liquids in terms of a solvent, and we compare them to a conventional ionic solution. So here you could just have potassium chloride dissolved in water. So a conventional ionic solution would have the ions which are dissociated and surrounded by solvent molecules. Ionic liquids are quite different. They have larger ions, and as you can see, there's no solvent molecules. They are both the ions and the solvent. So the interactions between the ions here are much different to conventional ionic solutions. And ionic liquids can be very complicated because they have lots of solvent interactions, including some of these weak non-specific forces like van der Waals, solvophobic and dispersion forces, and some stronger interactions including coulombic and anisotropic forces, particularly the hydrogen bonds. When you change the structure as well, you can get some strong hydrogen bonding, and dipole-dipole electron pair donor interactions. So much more complicated than traditional solutions. And the diversity and the strength of these forces are responsible for the arrangements both in the bulk and at the interfaces. So there's a lot of research being done to look at how ionic liquids line up at electrodes, and also how ionic liquids structure in the bulk. From an electrochemical point of view, we need to understand the electrochemical windows of these ionic liquids. So an electrochemical window is defined as the operating potential range where there's no current. So if we then want to see an analyte oxidation or reduction here, we don't want to have a background here. So at the edge of this operating potential window, you'll see a steep rise in the current, both in the negative range and in the positive range. So this is the reduction of the cation, and this is the oxidation of the anion. And different ionic liquids will have different electrochemical windows depending on how stable they are to redox reactions. And you can see some different electrodes give different potential windows as well. So there's been a lot of work gone on to look at the stability of these ions to electrochemical oxidation and reductions. In terms of being a solvent, they are also very highly conductive, and they are highly viscous. So I'm going to show in the next couple of slides some numbers just so you can compare them to traditional solvents. They can also be employed as a supporting electrolyte, so you can dissolve them into a solvent and you can have the ions solvated by that solvent, for example in acetonitrile. So if we take a look at some numbers of some of the physical properties, first of all, viscosity. So if you take the viscosity of water as 1. Some of the other organic solvents have a slightly lower viscosity. But you can see that different ionic liquids, and as you change the chemical structure, you can see that the viscosity is about 1 to 3 orders of magnitude more viscous than traditional solvents. And so when you get to about here, you're looking at more honey type viscosity. And in electrochemistry, that's important because mass transport rates are lowered. And what that means is when a species is diffusing through our ionic liquid to get to the electrode, that diffusion speed is much slower in a more viscous solvent. So if you take ferrocene, the diffusion coefficient of ferrocene in acetonitrile is about 10 to the minus 9 meters squared per second, and then that reduces by 2 to 3 orders of magnitude in these more viscous ionic liquids. Conductivity is also important for electrochemistry. So here you can see a table of conductivities of some conventional solvents, and the star shows that they're actually containing a dissolved supporting electrolyte. This is tetrabutyl ammonium perchlorate. So you can see these numbers. They're actually quite comparable to the conductivities of ionic liquids. And so you would think that ionic liquids, because they're made entirely of ions, that they would be really, really conductive. But because you have this high viscosity, you've got a balance between the conductivity and the slow rates of mass transport. The advantage of using ionic liquids in this case is that you don't have to add supporting electrolyte. So this can simplify your experimental setup and minimize your waste. So that's kind of a brief background on some of the physical properties of ionic liquids. I want to spend the rest of this seminar talking about how we use them as electrochemical solvents, and then some of the things which we have done recently. So I think the video gave you a good idea of some of the applications of our sensors. But we do need to be able to monitor gases, for example, looking at air pollution, occupational health and safety, particularly in enclosed environments where toxic gases might be released. For human health, so you can have gas sensors that can detect gases exhaled in the breath of patients who have, for example, liver disease. And also, you need to be able to detect explosive gases before they become dangerous. And there's a few different methods of gas detection, but one of the more commonly used one in industry is amperometric gas detection, particularly these kind of personal type monitors. So a user would take this handheld device, they will press a button on the side of the device, and then they'll get a readout of the concentration of whichever gas they're trying to detect. And so the sensor itself is here. So you can see a closer up version of the sensor. There's a gas permeable membrane on the top where the gas goes through, and then there's a plastic housing and 3 pins at the bottom. And so the 3 pins actually connect up to the 3 electrodes inside. So we have a sensing electrode, which is our working electrode, the reference and the counter. And this design normally has a liquid electrolyte, and it's usually sulfuric acid water mixture. So the drawbacks of this design is that it's very hard to miniaturize, so you still need to use quite a lot of expensive material, and it's usually platinum. So these electrodes are very hard to make low cost. And because of the use of a volatile electrolyte, in particular in hot and dry conditions, this can evaporate and the sensor no longer works. So using this non-volatility property of ionic liquids, my group and I, over the last maybe 8 or 9 years, have been trying to change the design of these traditional sensors and move towards a miniaturized design. And this way we're actually removing the membrane. So the difference in this case is that in the traditional sensor design, you have the gas that comes through the membrane and reaches the electrode where you have a redox reaction. In our design, you actually have the gas coming through the ionic liquid first and then diffusing towards the electrode. So a closer up image of our design, you can see these are commercially available devices. They're about $5 a unit, so much cheaper than the commercial sensors. They have very thin layers of pure metal. So this is gold working electrode in the middle, surrounded by a platinum counter and reference. So looking at the side of this planar device, you'd have the metals deposited onto the glass substrate, and then we will drop a microliter droplet of ionic liquid. So we can get away with about 0.5 microliters, so really small volumes. So in our experiments, we then have a gas flowing continuously over the ionic liquid. We have a partitioning step where the gas then dissolves in the ionic liquid. And then once we have equilibration here, we can apply a potential to oxidize or reduce that gas. And so if you go back to the kind of theories, the undergraduate thermodynamic type theories, if you have gas in the gas phase and gas in the liquid phase, you'll be at equilibrium in this case. If you increase the pressure of the gas or increase the concentration, then you'll force more of your gas molecules into the liquid phase until you're then in equilibrium. So you need to be in equilibrium, so then you're actually measuring the concentration of the gas in the liquid phase. But that's related to the concentration in the gas phase. And it's really important for us, because we're actually having our gases diffusing through the liquid, that we need to understand how gases behave both in the bulk and also right near the electrode, because all of the electrochemical reactions take place in a very small area above the electrode. So I've put here, does the choice of ionic liquid make a difference? The short answer to that is yes. I'm not going to talk too much about that here, but there's a huge number of ionic liquids available, so how do we make the best choice? So that's the topic for another day, but I should say it's actually very hard to predict which ones will be the best and which ones will not work, because for some gases, one particular ionic liquid is the best, and you expect it to be the same for the other gas, but it's different. So there's still quite a lot of trial and error in choosing the right ionic liquid. The electrochemical double layer in ionic liquids is really important as well. You'll have a structure of your ions in the bulk phase, but you'll also have a different structure of your ions near a charged surface. So if you put an electrode into a normal solvent, a traditional solvent, and you apply a potential, so in this case a negative potential on the electrode, the traditional theory of the electrical double layer shows that the ions will be solvated, and generally you'll have a layer of the oppositely charged ions to the electrode surface. But you have lots of solvation, lots of movement of ions. Whereas with ionic liquids, this is a big oversimplification, but if you apply a negatively charged potential, you will have positively charged cations line up on the surface, and then you can have these alternating layers of positive, negative, positive. As I said, it's quite an oversimplification. There are different cases where you can have what's called crowding and over-screening. So in this case, over-screening could mean that you might have two layers of cations to balance the charge at the electrode. But what's really, really important here is that the structure here is much more dense than the structure in the bulk. And so if you think we've got to get our analyte gas coming through the bulk, but also to the electrode surface. So does the diffusion coefficient or the solubility of that gas change in the double layer compared to in the bulk? I should mention that we can only detect redox active gases using our method. So we've done that using gases like oxygen and hydrogen, and we've also looked at a number of other more toxic gases. And generally, in terms of solubility, the polar gases are highly soluble, and these non-polar gases, oxygen and hydrogen, they're still soluble, but they're much more moderately soluble. And I spent a lot of my early part of my research, like my DECRA project, was focused on understanding reaction mechanisms of these different gases at the electrode surface. And it's actually really important to do that before you do the analytical development, because you need to know if any products will be formed on the surface, because they could passivate your electrode. And then also particularly, you've got your working electrode reaction, but you'll have a counter electrode reaction as well, and to balance the cell. And often the counter electrode could involve degradation of your solvent. So you need to really understand what's happening at the electrodes. The good news is that ionic liquids aren't that different to conventional aprotic solvents. So generally the reaction mechanisms are the same in ionic liquids as they would be in, say, acetonitrile or DMF. So oxygen reduces by 1 electron to form superoxide. Hydrogen oxidizes by 2 electrons to form protons, and ammonia oxidizes irreversibly in this case by 3 electrons to form nitrogen and protons. So how do we actually measure our response for the sensor? So this is the analytical part of it. So we can detect any gas that's redox active, so it either gains or loses an electron. And when this happens, we see a current which we measure with our machine called a potentiostat. So in this case, you can see this is an oxidation process of a gas at different concentrations. And you can see if you plot the peak current here, and the peak current will be directly proportional to the concentration of the gas. So once you've calibrated your sensor, you can then take it into a real environment. You'll measure a particular current, and then you can relate that to the concentration. The current depends on a number of different factors. So I've written them here, but I think it's probably easier to show an equation. So I tried to minimize equations, but because this is kind of a phys chem talk, I thought I'd put one in. So this is probably one of the most widely used equations in electrochemistry. So it shows the relationship between the peak current and then some of these other parameters. And it says that the peak current is dependent upon some constant times by the number of electrons to the power of 3/2, the electrode area, the bulk concentration, the square root of the diffusion coefficient, and the square root of the scan rate. And so what we can do in our experiments is to improve a couple of these things. So the bulk concentration, which is the solubility of the gas in the liquid, and also the diffusion coefficient, how fast it moves to the electrode. And we can do that by changing the ionic liquid structure. We can also improve the current response by using larger electrodes, so we can change the electrode area. So that's going to be the focus of my RACI Phys Chem lectureship seminars. So I still have to do one at UWA, so if anybody wants to come along to that one, I can pass Terry the details and can advertise it. But I'm not going to go into too much detail about that, but I'll be talking about how we've done a few different things to modify both the electrode itself to try to either get a higher surface area, for example, by making high surface area or porous electrodes. We've also made these cauliflower type structures and dendritic shaped platinum. And we can also change the material of the electrode. So we can add some kind of functional group. We've deposited different metals such as gold, palladium, copper and silver. And I think it was last year or the year before, we also looked at metal organic frameworks as an electrode surface. And the other thing we can do is change the structure of the ionic liquids. So we can change the different ions, and this is the only part of the of my results I'm going to talk about today, is actually combining them with polymers to create these robust sensors. So if you think these kind of planar devices with a droplet of a liquid, they're not going to be very robust, especially if you turn the electrode on its side or upside down. So we've been looking over the last few years to either mix them directly with polymers. PMMA mixes very nicely with ionic liquids, and that's what this is here. So you end up with a kind of gelled material on the surface. We've also used this copolymer, which is quite hydrophobic as well. And then what's really interesting, and we've been getting the best results with, is polymerized ionic liquids. So I'm just going to spend a few minutes talking to you about why I think polyionic liquids are really exciting for robust gas sensors. So polyionic liquids are polyelectrolytes, and they combine these good properties of ionic liquids, which I've already mentioned, and the physical stability of polymers. They've been used for about 20 years in different applications, mostly for gas sorption and separation, and also in flexible electronics. But surprising to me, nobody's actually used them in amperometric sensors. So that's what we've been looking at over the last year or so. We've been collaborating with Professor David Mercer-Reyes at Polymat in Spain, and his former postdoc who's now moved to Lisbon, and they've been giving us some ionic liquids, polyionic liquids. So what you can see here is, in this case, the cation is polymerized, so these are long chains, and then you have an anion that's freely mobile. And you have to combine them with an ionic liquid to create a membrane that we can use for electrochemistry. And the reason you have to combine them with ionic liquids is that the polyionic liquids are solids. So we use 80 milligrams with 120 milligrams of ionic liquid into a vial, and then add a fairly large volume of acetone as a mixing and transfer solvent. And what you can see is on our electrodes, this is a really large polymer film, just to show you what it looks like, but we don't normally use that much. But once the acetone is evaporated, then you're left with this polymer film on the surface. And these are really interesting materials. They're much better than the normal mixtures of polymers and ionic liquids, because they're actually really peelable. So I've got a couple of students working on peelable films to pick up solid explosive materials or solid materials on surfaces, and then bring the material directly to the electrode by taking the side which was swabbed straight to the electrode. So in terms of gas sensing, though, they actually behave really nicely. So this is oxygen reduction. I've said before that you reduce oxygen to superoxide, so that's the reduction peak, and then this is the superoxide oxidation peak. What you can see here is, well, there's the calibration graph. You can see that as you add more polyionic liquid, obviously you're making it more solid-like, so you're going to reduce your sensitivity or your gradient of the calibration graph. But there's no change in the peak shape, so we're not seeing resistance and things like we did with some of the other polymers. And in fact, I'll show you more on the next slide, but the blank signal is actually cleaner the more polyionic liquid we add. And we think that's because it's much easier to purify solid materials, so polyionic liquids can be purified easier than liquid ionic liquids. And this has actually meant that we can get lower limits of detection for oxygen, which is good, but the real important thing is that we can get lower limits of detection for toxic gases, where we need to be able to detect really small concentrations. So for sulfur dioxide, you can see from the pure to the polyionic liquids mixtures, we also see a similar kind of no change in shape. And it's a bit more clear here. The pure ionic liquid has this impurity peak, which we can see more because we're at low concentrations. And then that impurity peak cleans up quite a lot. So we're able to see these lower concentrations much easier. And I'll also mention, you can see from this one that the peaks are shifting quite a lot. So we have an unstable reference potential, and sulfur dioxide is one of those gases that really shifts the reference electrode. So in the pure ionic liquid, we see quite large shifts, but you can see that these shifts are much less dramatic in the polyionic liquid. So we're still doing quite a lot of work on this, and we're also trying to commercialise this in the next couple of years. So we're also trying different polyionic liquid mixtures, because obviously I mentioned before there's a whole range of anions and cations. Some of the ones we tried do not form a homogeneous mixture. You can see the polymer and the ionic liquid phase is separated, and also in this case here. And this happened with the ionic liquids, which had these kind of more different chemical structures and more hydrophilic type ions. But out of 11 ionic liquids tested, the C4-MIM NTF2 was the best, and we have been now using this ionic liquid to then look at the effect of changing the structure of the polyionic liquids ion. And then just finally, I wanted to show you the application of our oxygen sensors in mining vehicle tyres. So we've been using these polyionic liquid materials on these small electrodes to detect oxygen gas inside these huge mining vehicle tyres. So you can see just how big they are. This is just a picture of me last year in Kalgoorlie. So why it's important is because I actually didn't know this before I started talking to some mining people, but these tyres, when they're filled with air or oxygen inside, they can actually be explosion hazards during lightning strikes, or even if you're doing welding on them. And that's because the oxygen inside the tyre, when it gets struck by lightning, it's flammable and explosive. And a number of incidents have occurred on Australian mine sites. For example, in a WA mine in 2018, one of these trucks was struck by lightning and the front tyre exploded. So what happens at the moment is the mines have to shut down during lightning storms because it's obviously too dangerous to be out. So the mines have an idea to fill the tyres with nitrogen, and that would reduce this explosion hazard. But obviously they need to make sure there's no oxygen getting in. So they need to have a robust sensor that's going to be able to go round and round in these tyres, and also in really hot, dry conditions like on the mines. So that's why my sensors are now being field trialled. So I don't know the results of them yet, but it's quite exciting to have a sort of homegrown application for the sensors. So to conclude, I hope I've shown you that ionic liquids are really interesting, and that we need to understand the fundamental behaviour of ionic liquids themselves, and how this affects species dissolved in them. This idea of solvation is quite different to traditional salt solvent systems, and then the physical properties like the viscosity is much higher and mass transport is slower. The conductivity means we can use the ionic liquids in the pure form. And we also need to understand how the behaviour at an electrode is different to the behaviour in the bulk. The choice of ionic liquid is very important, so I haven't actually talked about that in this seminar, but in my lectureship seminar I will talk a bit more about that. And then I did already mention that it's quite hard to predict which ones are the best. These polyionic ionic liquid mixtures make excellent, robust gas sensing materials, and I'm excited to hopefully see them being used on WA mines in the future. So I'd like to acknowledge my group members. This isn't my whole group, this is actually my group with Professor Rob Atkins' group, and there's a couple of people here in the audience who might be in this picture. I need to get a more updated picture for this year. But I'd like to thank Curtin Chemistry, School of Molecular and Life Sciences, and the ARC for funding all this research, and the RACI for the lectureship. And thank you all for taking the time to listen.
Cool. Well, thank you very much. A fascinating lecture there. Yes, fantastic to see some good chemistry actually getting commercialised and actually on their own doorstep.
Yep.
So, yeah, it's great. Let's open the floor to some questions. At the back.
Thanks, Debbie. Do you have any, what sort of response time do you get there with electrodes?
So for the polymer materials, we've actually tried to spin coat really thin layers, and we can get response times within a couple of seconds. But generally, for the sort of more stable sensors, it's at probably about 30, 40 seconds. The thicker the layer you have, the longer it will take. So very thick layers, you'll end up 5 to 10 minutes. So yeah, it depends how you design the sensor.
Like explosive situations, you want very fast response times.
Well, for the explosives, I think that's why this peelable film idea is actually quite good, because if you've got a solid on a surface, you can do it. Bring the explosive directly to the electrode, and then you can sense it straight away. So we did try a few things where we actually had an electrolyte on, so this was before we could peel them, but we had the PMMA ionic liquid mixture, and we turned the electrode over and swabbed and turned it back, but then we had to wait for the explosive to diffuse through to get to the electrode, and that was about 30 minutes to wait. So having an instant response, like using these peelable materials, I think is the best way to go.
Do you have a hydrogen cyanide sensor, do you?
I haven't looked at hydrogen cyanide myself, no.
I'll be here.
You have a question?
Great talk. I was wondering if you were going to mass produce these for, I don't know, for whatever application, could they be pre-prepared with the ionic liquid or polyionic liquid on the surface, and then you have it sealed in some sort of little, something you peel off, I think, and then it's ready to go?
Yeah, so like working with the company that I'm working with, I'm actually seeing the other side as well, because obviously my mind is just on the fundamentals and what's happening, but I'm seeing how they actually do things. And yeah, when this becomes like in the production line, then yeah, they will do some kind of screen printing or printing of the material on the surface, so that you get like fixed thicknesses of that. And yeah, I think it could be fully automated. It's a good idea to have something on the top to kind of protect it until it needs to be used.
If you want to have it sealed so no air or contaminants can get in, and when you're ready to use it, you just peel it off.
Yeah. Yeah, so I haven't thought about that, but that's a good idea, yeah.
A couple of things. In a previous life, I worked for Rio for about 30 odd years, and there's two things. You're right about your lightning element. Also, if we had a truck go under an east radio overhead power line, so what you immediately do is put a 100 metre radius around the truck, and no one goes with it for 48 hours, because that reaction does take a long time. So an oxygen sensor in that may be a lot of value. The other one is also, I used to do gas freeze on ships, where you had to know the oxygen level. Either put people down, or in the slops tanks, the oxygen had to be below a certain level. The other one, of course, was the LEL, which is a lower explosive limit for methane, ethane, and so on.
Yep.
I assume it won't work on hydrocarbons like that. They're not polar.
Yeah, so
obviously, your nitrates and stuff are explosives, but at least a mixture of oxygen and air and hydrocarbons at low levels.
yeah, hydrocarbons they're a little bit harder to detect because they're not redox active, and so there's been a little bit of research looking at methane with oxygen, and they had like some some reaction happening to be able to sense the methane, but it's a lot more difficult. I've only been focusing on the redox active gases for my stuff, but yeah, it would be good to have a good sensor for that.
Sensor with it, which gives you LELs and oxygen and whatever else, but your detectors may in the future be able to replace the fairly expensive
Yeah, and I think probably the biggest or the extra thing that my sensors could do is be used in more extreme environments as well. So that's what I'm hoping. Like, our sensors might not be the best for all the other applications. There's already good gas sensors out there, but if we target specific applications, then I think there's a lot of benefits of these.
Yeah, in the case of the oxygen sensing in that tire, it's actually ideal, I think, because there's just oxygen in the bulk of nitrogen. But what happens if we try to use it for pollution gas sensing? Is it selective enough to target that one?
So for the tyre sensor, they told me that they need to make sure the oxygen level doesn't build up above 5%. 5% is doable in ionic liquids. If you try to go to really low concentrations, then it's much harder because you've got this high viscosity that lowers your current response. For the pollution type sensors, typically the pollution is at like very, very low concentrations, so it's probably too hard for our sensors to detect. We're more looking at the kind of exposure limits and things for the toxic gases. So we can get down to ppm and sometimes to ppb, but often not quite enough for the pollution sensors.
Could they work in the stack, the chimney stacks, like where it's highly concentrated?
Yeah, so in fact I think that's a good application of ours as well, is that we don't see like a saturation of the sensor. So we tend to see the calibration goes all the way up to the high concentrations. So depending on what gas it is, but yeah, generally I think they would work nice at high concentrations.
So things like chlorine and H2S would be very applicable to your system?
Yeah, so I mean, I've actually got a student who's just going to start on the H2S, but we've looked at chlorine as well, and it depends on what application you want it for as to what concentration range you want to measure. But yeah, we've been measuring down to the permissible exposure limit, and it's been working quite well. Yeah.
Does your electrodes take you to atmospheric levels of oxygen? The idea of, well, the thought is that in a lot of instances in petrochemicals and such like, they sweep a vessel with nitrogen to start with, and then they have to purge it with oxygen or with air to allow people to enter into it.
Yeah.
And I worked on a plant where they checked that there was no explosive gases or anything, but they didn't check for oxygen. The guy went in and he very nearly died as a consequence of it. So is there an application for checking, because you obviously need to be able to go at some distance away from into the centre of the vessel?
Yeah, so I think that these type of sensors would work really nicely there. So as I said, for the tyres you want about 5%. For like entering a room you want it to be close to 21%. Yeah. And we've actually shown our sensors can go up to 100%. The higher the concentration we have on the sensor, if you're doing a long-term, I didn't show any results here, but if you do a long-term measurement of the current, you can actually start to see a decay in the signal because you're continually producing superoxide. But if you're just using it as like a quick response rather than a continuous sensor, then easily can go the whole range, like 0.1 to 100%.
So I think we're done for questions now, but yeah, thanks again, Debbie, for your lovely talk.
Thanks, Terry.